recall that the cardinality of a set, which we denote using what looks like absolute value bars around the name of the set, represents the number of elements in that set. And you'll also recall that when we talk about the union of two sets, we're saying take two sets and just sort of squish them together into one big set. And so in some ways, we think about set union as adding two sets together or just combining them together in some way. However, it's not as simple as saying that if we wanted to find the cardinality of A union B, you can just add the cardinality of A plus the cardinality of B. This is not necessarily going to be the case. To give you one small example, let's look at the sets that we saw in the last videos. So A is a set containing 1, 2, 3, 4, and 5. B is a set containing 3, 5, 6, and 7. All right, well, the cardinality of A is 5. The cardinality of B is 4. Is the cardinality of A union B just going to be equal to 5 plus 4? No, right? Because A union B is going to consist of the elements 1, 2, 3, 4, 5. We already have 3, we already have 5, 6, and 7. It has 7 elements. You can see it clearly has 7 elements. So it's not the case that you can just add up the individual cardinalities to get this here. Why? Why is that a problem? Well, think about what the Venn diagram looks like. Here's A, here's B. We had 3 elements over here, 1, 2, and 3. Or sorry, 1, 2, and 4. So I'm going to do a cardinality Venn diagram here. So this is just representing how many elements are in this section of the set A minus B. We had 2 elements that were in both sets, and we had 6 and 7. We had 2 elements that were in B but not in A. So when you add up these individual parts of it together, you'll get the total number, right? 3 plus 2 plus 2 is equal to 7, the cardinality of A union B. But if we were to just add up 5 plus 4, we would be adding the cardinality of A, right? We'd be adding up this part right here, 3 plus 2 is 5, plus the cardinality of B, that's going to be this here. So by just adding up the cardinality of A plus the cardinality of B, you accidentally add in this middle section twice. We accounted for those 2 elements twice. And so a way to sort of fix this equation to make it true would be to say, well, in a way, you can start off by adding all the elements of A plus all the elements of B, but you're going to overcount that way. Anything that's in the intersection is going to get counted twice. So if we just go ahead and subtract the cardinality of the intersection, that should give us a cardinality of the union. So let's make that a little bit more clear. We call this a principle of inclusion-exclusion, sometimes shortened to PIE, P-I-E. For finite sets A and B, you can find the cardinality of A union B by starting with the cardinality of A, adding the cardinality of B, but since you've double counted that intersection, you now need to subtract the cardinality of A intersect B to correct for that overcounting. This is a common counting technique that we do, sort of overcount and then correct for it later. And we can check and see that that's true in this example up here. We said there were 7 elements in A union B. That's the same as starting with all the elements of A. There's 5 of them, plus all the elements of B. There's 4 of them, minus everything in the intersection. There were 2 elements of the intersection. Okay, so this checks out here, right? Now, notice that this equation up here, which was actually not correct, could be correct, provided that the intersection was empty. If there's nothing in common with the sets A and B, then yeah, this is going to be true, that the cardinality of the union is just a cardinality of one plus a cardinality of the other, because you don't accidentally do any overcounting if the 2 sets have nothing in common. But in general, when we're trying to find the cardinality of the union, we need to use the principle of inclusion-exclusion. So let's look at an example. Suppose in a class of 25 students, everyone is majoring in math, computer science, or both. Suppose that there's 21 students who are computer science majors and 12 students who are math majors. This is just saying that each one of these 21 students is going to get a degree in computer science. They might also be getting a degree in math though, right? They might actually lie in both of these sets. Similarly, there's 12 students who are getting a math degree, but some of them might be CS majors. How many of them are double majors? Well, we can use the principle of inclusion-exclusion here to find out, right? So let's let C be the set of computer science majors, and let M be the set of math majors. then we would have that C union M is the set of students who are CS, math, or both. And the intersection, C intersect M, those are going to be the students who are in both of those sets, who are computer science majors and also math majors. So these are your CS math double majors. So by the principle of inclusion-exclusion for these two sets, we have that the cardinality of C union M should be equal to the cardinality of C plus the cardinality of M minus the cardinality of the intersection, computer science and math majors. So how many of them are in the union? How many students are CS majors, math majors, or both? Well, that they sort of told us at the beginning that there's 25 students in the class and everybody's going to fall into at least one of those categories. So this is going to be 25 because there's 25 students in the class. The cardinality of C is the number of computer science majors, it's 21. Cardinality of M is 12. And so this is what we're looking for. The number of students who are double majors is cardinality of C intersect M. So I'm just going to call that X for now because it's a variable we're trying to solve for. So we add these together, we get, let's see, 33 minus X. All right, 25 is equal to 33 minus X. It looks like X is going to have to be equal to 8 here. Right, solving this linear equation gives us that X is equal to 8. And so there's going to be 8 students or both. And we can check and make sure that this makes sense in a Venn diagram. If here's your computer science majors and here's your math majors, this is saying that there's got to be 8 people in the intersection. There's 8 people who are in both. And so that means in total, if there's a total of 21 computer science majors, 8 of them are already accounted for, which means we've got 13 students who are just computer science majors, right? 13 plus 8 gives you the total of 21. Similarly, there's 12 math majors altogether, so there's 4 students who are just math majors, but not computer science. If we wanted to fill in this Venn diagram right off the bat, we wouldn't necessarily know, how to split up these 21 students and these 12 students without using the principle of inclusion-exclusion. So let's look at another example. Suppose that there's a total of 320 math majors at BSU. If 90 of them are taking a computer science class, 75 of them are taking a physics class, and 40 are taking both, how many students are taking neither? How do we use the principle of inclusion-exclusion here? Well, maybe it would actually help with the Venn diagram. Let's start there. So we've got students taking computer science, we've got some students taking physics, and we have 40 students taking both. So I'm going to put 40 here because there's 40 students taking both. Now what am I going to put over here? Well, there's 90 students altogether who are taking computer science. 40 of them are already accounted for because they're in this intersection, they're in both, which means there have to be 50 students who are out here taking just computer science without taking physics. Similarly, if there's 75 taking physics but 40 are accounted for, there have to be 35 over here taking just physics but not computer science. Now, what does this tell us? Well, either by principle of inclusion-exclusion or just by sort of looking at the diagram directly, the union of the students taking computer science or physics, the number of students taking one or the other, is going to be 50 plus 40 plus 35. Right? We could have done principle of inclusion-exclusion directly and just said 90 plus 75 minus 40 as well. But this is going to give you 90 plus 35, that's 125 students. So how many are taking neither? Well, here we'll have to use subtraction because there's a total of 320 math majors and 125 of them are accounted for, which means out here in the box, if this box is the universal set of math majors, there's going to be 320 minus 125. That's 195 that are not accounted for. Right. So 195 students are taking neither. Okay. So the reasoning that we had to use here is the idea that if you know the larger size of the universal set and you know how many elements are in some particular subset, then you can subtract to figure out how many elements are not in that subset. And that gives us the cardinality of the complement. So the cardinality of the complement tells us that if A is a finite set within a finite universe U, then the cardinality of A plus the cardinality of A complement is going to be equal to the cardinality of the universe. Right? That makes perfect sense if you think about the Venn diagram. Here's A. A complement is everything outside, right, in this box. So this is saying if you add up all that blue shaded space and then you add up the cardinality of A, you're going to get the entire universal space, right? You get everything. And so another way of writing that is just to say if you wanted to find the cardinality of A, sometimes it's easier to find the cardinality of the whole universe and then subtract the cardinality of the complement. Or alternately, if you wanted to know the cardinality of the complement, take the cardinality of the universe and subtract the cardinality of A. If you have this information, sometimes this is easier to use. So, for example, in one of the warm-up problems, we needed to count how many of the cubes did not have paint on it. And so you know in total there's 27 cubes. So if we just subtract off the one cube that did not have paint on it in the middle, that one, you'd be left with 26 cubes on the outside that do have to have paint on it, right? So we use this idea of finding the cardinality of the complement often. This is just sort of making it a little bit more formal. All right, now the last thing that we want to talk about is applying the principle of inclusion-exclusion to more than two sets. So if you have finite sets A, B, and C, and you wanted to find the cardinality of the union, is it just going to be as simple as saying the cardinality of A plus the cardinality of B plus the cardinality of C minus the intersection of all three? Unfortunately not, right? So the principle of inclusion-exclusion doesn't extend quite so simply to more than two sets. Let's think about what would happen if we did try to do that. I'm going to need some colors for this. Right, we're going to try to find the cardinality of the union. How many elements are in all of these sets altogether? Well, we can start off by saying the cardinality of A plus the cardinality of B plus the cardinality of C. But then we need to make some corrections just like we did for principle of inclusion-exclusion for two sets. Right, so here's our cardinality of C here. So we've accounted for all of these. We've accounted for all of B. And we've accounted for all of A. Let's see, we'll do it like this. We can see that some parts of this diagram have been counted more than once. Right, this sort of intersection here has been counted multiple times, this intersection here has been counted multiple times, this one here, etc. And so we don't want to count things multiple times, so we need to subtract in order to account for the double counting. Right, so as an example, I want to take out the intersection A intersect B, because I counted it twice. I counted it for A and I counted it for B. Similarly, I want to subtract A intersect C because I accounted for that twice with the purple and the green. And I want to subtract B intersect C because I counted that twice as well with the green and with the red. But here's the problem. There's one section right in the middle that hasn't really been accounted for at all. If we look at this part in the middle, way down here, I counted it when I counted A, and again when I counted B, and again when I counted C. But then I subtracted it when I subtracted the intersection of A intersect B. I subtracted it again for A intersect C, and I subtracted it again for B intersect C. So if there are any elements that are in all three of these sets, they've now been counted 3 times, but then subtracted 3 times. So they have not been accounted for at all, which means we really need to add back in the 3-way intersection, A intersect B intersect C, all over again. So this is a principle of inclusion-exclusion for 3 sets. If you want to find the cardinality of the union of all 3, add the cardinality of A plus the cardinality of B plus the cardinality of C. Subtract each of the pairwise intersections, A intersect B, A intersect C, and B intersect C. And finally, add back in the intersection of all 3 sets. So let's do one more example. Suppose we have all 25 students in a particular class own a cat, a dog, or a ferret, or possibly more than one of these. And let's say we know that 11 have a dog, 13 have a cat, 9 have a ferret, but those students might also fall into one or more of these categories, right? Some of these dog owners might also have a cat, etc. And so we know that 4 of them own a dog and a ferret, 2 own a cat and a ferret, and 3 own a cat and a dog. How many own all 3, and how many own only a dog? So let's try to use the principle of inclusion-exclusion here. So I'm going to say D is the set of students who own a dog, C is the set of students who own a cat, F is ferret. And so the students who own a dog and a ferret, that's going to be your D intersect F. Cat and a ferret will be C intersect F, and cat and a dog will be C intersect D. We want to find how many own all 3. We want to find the intersection C intersect D intersect F. So according to the principle of inclusion-exclusion for 3 sets, we should have C union D union F is equal to the cardinality of C plus the cardinality of D plus the cardinality of F minus C intersect D minus C intersect F minus D intersect F. Finally, plus, right, we add back in the 3-way intersection at the end. C and D and F. Running out of space here. All right. So what is the union of this set going to represent? Well, this is going to be all the students who have a cat or a dog or a ferret, or maybe more than that. But that's just all of the students, right? They told us everybody owns at least one, so we know that the size of the union is 25. Now we're going to use this information here to fill in the rest of this. Cardinality of C is 13, cardinality of D is 11, cardinality of F is 9. We're going to subtract the intersection. C and D is 3, C and F is 2, D and F is 4, and finally we add back in the 3-way intersection. This is what we're looking for, so I'm just going to call this X, because that's what we're trying to solve for. All right, so what do we get then? We get 25 is equal to 13 plus 20, so this is going to be 33 when you add these together. Minus 3 minus 2 minus 4, so it's going to be minus 9, and then plus X. So we have 25 is equal to 24 plus X. Solving for X gives us that X is equal to 1. So 1 student owns all 3. So we were able to directly use the principle of inclusion-exclusion to solve that one. But they also asked us how many students own only one dog, right, or only a dog. So to figure that out, it's going to be useful to use a Venn diagram. So I'm going to take what I just found out and use that to build a Venn diagram for this particular problem. So let's call this my cat circle. This is for dogs, and this is for ferrets. I just used principle of inclusion-exclusion to determine that 1 student owns all 3. So there's only 1 student that falls in this 3-way intersection here, right? But we want to know how many own just a dog, right? We want to know how many are in this section right here. All right, well, I know that the students who own a cat and a dog, that's this area of the Venn diagram right here. The students who own a cat and a dog, that there's 3 of them. 1's already been accounted for, and so there have to be 2 students up here, so that this intersection, C intersect D, actually has 3 students altogether. Similarly, for dogs and ferrets, for this sort of football-shaped region here, we know that there's 4 students who own a dog and a ferret. 1's already been accounted for, and so we have to have 3 here, so that in total there are 4 students who own a dog and a ferret. And now finally, since 11 students own a dog altogether, and 3, 4, 5, 6 of them are already accounted for, it has to be that there's exactly 5 out here in the dog region, right? There's 5 who own only a dog. And the best way to see that really is to draw out the Venn diagram. So you could also use that to figure out how many own just a cat or just a ferret, or a cat and a ferret but no dog, right? Using the same idea here.